I've been thinking about it for a few days and I've made the decision to switch to GODOT 4. I was motivated by the release of the Beta 2 version, even though I've read in different sites that it's full of bugs, which is pretty obvious. Drawing angles. Let's start with the basics. Draw a distance field based on an angle. This will be useful as a practice to draw polygons and later work with polar coordinates. As you can see, it is about using the x and y coordinates into the item function to get an angle. In this example, both the coordinate 0.5, 0.5 and the coordinate 1.0, 1.0 give us the same angle. This is quite easy. However, if we want a more meaningful angle, we have to do some operations, like remapping the UV coordinates, which we have already done before. Then normalize the angle. This is dividing it by 2 pi or tau, that is the same. This way, we get an angle between minus 0.5 and 0.5. Afterwards, we add 0.5 to get an angle between 0 and 1. So let's create a new node 3D and inside it a mesh instance and then a plane. As we can see in GODOT 4, the material is located one level deeper. For that reason, we're going to use the surface material override option. This might not be a valid reason when you develop a real game. We create a new shader material and then a shader. Give it a meaningful name. I created a shader folder. I named it angle. And now we create a float variable to store the conversion of the UV coordinates. We use the item function and we assign it to albedo. This way, we have an angle drawn as a distance field. Now, let's remap the UV space and then use the item function with the new coordinates with negative values. We assign them to angle. And as you can see, GODOT 4 shows a glow effect on values that are outside of the color space. Now that there is a larger range in the angle, it shows values higher than 1.0. Let's normalize the angle by dividing it by the tau constant to return values between minus 0.5 and 0.5. These values are still not useful because there are some values lower than 0, so we have to add 0.5 to get the range from 0 to 1. Thus, we must add 0.5 to the angle, and by doing this, we have drawn the full angle of 2 pi or tau. Now we're going to use the cosine function, which is drawn in polar coordinates when applied to the angle. We don't see any result because we have to increase the period of the function. So I'm going to multiply the angle by 10. Now we have this interesting effect thanks to the cosine function that goes between values of minus 1 and 1. Now let's multiply by 100 and we have as a result this kind of star, and as you can see, it has a smooth interpolation between the values because of the cosine function. Now we apply the step function, which, in addition to giving us sharp edges, normalizes the values provided by the cosine function. Okay, now we have solid edge, and even we can add animation to this shape by adding the time variable. And there we go. Drawing polygons. Here we are again in the GODOT shader space, and we will review this function to create polygons. We can identify some familiar stuff like the tau constant, the UV remapping, gating the angle using eta, and the next line is a new one, which is just dividing tau by the number of sides. This line is a bit tricky, so we will discuss it later. And the step function to draw the polygon from the distance field, and finally return the result as a vec 4 that will be an RGB color plus the alpha component. So I just created a new plane and I just copied and pasted the function from GODOT shaders and modified the output value to be a float. And pass to albedo. So we have the polygon and we can change the size. Now let's analyze the function that returns the distance field to create your polygon. What I did is to copy the function in this graphing calculator. We have the cosine of 0.5 plus the angle divided by the radius times the radius minus the angle, and finally we multiply by the length of the UV vector. I used some variables like the number of sides, the radius, that is a quotient of tau divided by the sides, the width of the vector UV, which I set as an input variable that I can manipulate, and as you can see, here is the function that draws the distance field. Notice what happens when I change the size of the UV vector. It changes the shape of the output function, and when I change the number of sides, these are represented as little jumps in the function. For example, 3 jumps correspond to 3 sides of the polygon. If I change to 5, you have 5 jumps. With 6, it's the same. And the most important aspect is that there is no smooth interpolation between the curves. There is an edge. If you notice, this is quite different from the original cosine function, where we have a smooth change between the values. If we remove the step function, we can see the smooth interpolation of the cosine function. Now, everything mentioned before makes more sense if we plot the function in polar coordinates, because when we use the item function, we convert to this. First of all, here we have the shape that we have already drawn before with the cosine function, and we can also modify the number of branches of the shape, so to speak. And now, let's see the function that draws the polygon plotted in polar coordinates. It is exactly the same function, and now those little jumps turn it into circular shapes. Above I set the parameters, and if I change the length of the UV vector, it changes the size of the shape, and if I change the number of sides, then the number of circular shapes changes as well. As you can see, this will be the distance field of a triangle. Something interesting is that a two-sided or one-sided polygon returns an output, which doesn't make any sense in a polygon, but it does in this function. Now, if we go back to the shader and draw a one-sided polygon, we see that indeed a shape is drawn. We change to 2 sides, we have a kind of rectangle, and we also see the distance field. Finally, drawing a 3-sided polygon, we see the distance field that corresponds to the function that we revised in the graphing calculator. Now, notice that the angles of the shape are much more pronounced when plotted in polar coordinates. This is the same for other polygons. Also, by changing the size of the UV, we see how the distance field will be drawn in our shader. In the same manner, we can draw the square, which is exactly the same distance field and the same shape as using the previous technique of reflecting the UV map. Polar coordinates. Polar coordinates are all about mapping the x and y coordinates to another based on angles. We have already been doing it, but now we're going to map the whole UV map. As we can see, the x coordinate is mapped to the size of the radius that is equals to the vector size resulting from the difference of the current UV coordinate and the center. The y coordinate is mapped to the angle returned by the item function. Finally, we see the result of mapping the UV coordinates. Again, let's go to the GODOT shader site and take a look at the function to map the polar coordinates. First, we have the direction vector, which is the difference of the current UV coordinate with the center. Then we get the distance and multiply by 2 to match up the original coordinates. Then we get the angle with the eigenfunction and divide by tau to normalize it. Finally, we use the mod function, which is used to create patterns, and this is a topic that I will explain later. Let's go to GODOT, and now I'm going to duplicate the plane and create a new material shader, and inside it a new shader. I'm going to name it polar chords. Next, I'm going to copy the function from GODOT shaders and remove a couple of parameters which perform additional actions to the polar coordinates, which I don't need to explain now. I'm going to remove those parameters inside the function, and I will also replace the hard-coded values by the constant tau that the version 4 of GODOT provides. Now I'm going to declare a vector2 variable to store the polar coordinates. I'm going to pass the UV chords as parameter and specify where I want the center to be drawn. Then I assign it to albedo, and now we can see the output. The result works, however, isn't exactly the same as using the mod function. So I will replace it with an equivalent function, which is the fract function, and now we have the same output. Now, having the UV coordinates transformed to polar coordinates, I'm going to load a texture using them. So I declare a new uniform sample variable, call it text. I will assign the GODOT icon into the shader parameters, and now I get the image with the texture function using the new coordinates. And well, this is not the output I expected, as I am using the old coordinates. So I use the polar coordinates. And there we have it.